Hi, my name is Iago Breno, and this is the presentation for the paper The Impact of Real Rain in a Vision Task. The presentation is structured as follows. First, in the introduction, the motivation and the goal are discussed. After that, I will explain our proposed approach, followed by the result and discussion, and finally the conclusion with remarks and future work. Single image deraining is a task that, given a single image with a rainy scene, the goal is to remove the rain artifacts to enhance the visual quality of the image. In the last few years, important progress has been made in deep learning. However, there are some limiting aspects that we believe should be addressed in this task. Here we have a list of some of them. First, the majority of the works only consider dealing with the rain streaks, simplifying too much the dynamic weather where you can have rain mists and raindrops, for example. Another point is the common approach that relies heavily on synthetic dataset, which does not capture the complexity of the real rain. Besides, the image quality is usually of high resolution, and the potential benefits for high-level vision tasks are not considered systematically in the literature, where the focus goes more on the image restoration perspective. Considering all these unsatisfactory aspects, the goal of this work is to understand the impact of the real rain in a real setting where we have low-quality rainy images, variety of rain intensity, and the perspective exposed towards understanding how the rain impacts a high-level task. In this work, we are evaluating the impact on object detection. The figure depicts our strategy. We consider the rain effect in the image quality as the degradation factors in our real setting. As we can see, we have different scenarios with increasing levels of degradation going from high-quality sunny to low-quality heavy rain. In this way, we can evaluate the contribution of each factor given the variations from the scene. So, in more detail, we have 5,762 urban scene images. They were partitioned in the following four subsets, as you saw previously in the figure, and all the images have main annotations for the most common objects in the dataset: car, person, bus, truck, and motorcycle. The number of objects per class were proportionally balanced between the subsets, and only daytime images were considered to not include other factors like cloudy aspects in the nighttime scenes. Using the proposed dataset, we applied faster CNN and RetinaNet over each partition in two perspectives, pre-training and fine-tuning. The results were evaluated using MAP, and with that, we could draw comparisons of the impact of the degradation caused by the factors. So, these are the results. The table shows results for the two detectors in pre-trained and fine-tuned scenarios. The best results for the detectors in each scenario are highlighted. First, for the pre-training perspective, we can see in the first line for each detector that the performance decreases as the scenarios increase in terms of degradation level. This indicates that the image quality in the rain contributed to the impairment of the results as expected. For the fine-tuning results, we can observe that the model substantially improved on the respective scenarios, achieving similar results between them, regardless of the variation in the rain intensity. When comparing these results with the pre-trained models on high-quality sunny scenario, a large gap was still observed. This indicates that the image quality is a more dominant factor. So, for the pre-trained models, the results were in accordance with the individual perception. For the fine-tuned models, the rain intensity was not a problem for the model, but the image quality is still imposed a challenge given the observed gap between the high-quality scenario and the low-quality ones. Summarizing, it is important to approach the task accommodating the realness of the rain in our view scenario and evaluate how the rain is impacting the performance of a computer vision system in a practical application. In this work, we saw that the image quality is a more challenging factor with the models achieving similar results when fine-tuned in the scenarios regardless of the distinct rain intensities. Finally, a supervised strategy would be too costly considering the complexity and variation of the rain. So, for future work, we believe that one important direction is unsupervised learning to cope with the domain shift caused by the rain. Thank you.